All right, guys, here we go. Section 1.5. Two things we're going to be looking at here. We're going to look at parametric relationships. That's just going to be this first page, and then for the remainder of the lesson, we're going to be looking at inverses. So that's what we're going to focus more on. We don't do a ton with parametric relations. There is a need for this later on down the road, so we're kind of introducing this idea now. Parametric relationships really just have to do with instead of defining a function in just terms of y and x, they are separately defining how you would find the x's. So they're saying x's can be found by doing t minus 1. So it's like they're throwing in a third variable here. So a little more exciting. And they're going to define the y coordinates as t squared minus 1. So one of the first things they're asking us to do so we can kind of put these numbers together to make a little more sense out of it is let's just give all these values for t and start plugging them in so we can get some relationships going here between our x's and y values. So if I were to go down the list and plug in all those numbers into t minus 1, then that's going to give me some x coordinates. And as I plug in those same numbers for t squared minus 1, I'm going to get the y coordinates that go with them. And so that's what you're seeing right here in this table. Get it, and hopefully make this clear for you. So that's what you're seeing within this table. So these were the values for t. Plugged them in for the x's, in for this t to get the x values. Plugged them in for this t to get the y values. And if we put those together, we can create the ordered pairs that make up this function. So we could come up with a graph by plotting all of these points, but it's going to be easier and make a little more sense if we can go another step with it and actually get a function in just terms of y and x. So one of the things they're going to do here is they're going to say, okay, well, we know that y is t squared minus 1. So what we're going to do is we're going to define t by adding this 1 over to the other side. And they're going to say t equals x plus 1. And we're going to sub in x plus 1 for that t right there. Right? And so we're going to get a function now in just terms of y and x. And we could actually graph it from here. This is something that we've identified in the past. We did this in Algebra 2 as something called vertex form of a parabola, where my vertex becomes -1, -1. And so that's where you're getting the vertex right there. We could also clean this up. We can square this, bring down your -1, combine like terms, and you get the function this way as well. So this is another way we could see this parabola. So if we graph this function, it should match up with these data points should be on that curve as we graph this parabola. But typically it's easier to graph a parabola as it's written like this rather than by just plotting a bunch of data points. We could take this, graph it in our calculator, and our calculator would actually give us all of the data points that we would want. And so I'll show you that here on the next example that we're going to do. All right. So the other thing they were kind of asking us to do with it would be to make that graph. So once we've identified what the function looks like in terms of y and x, now we could graph it in terms that we're a little more used to in terms of just y and x. So let's do one of these together, and then we're going to move on to inverses here. So I kind of already laid out a table for us that we can use. So similar to the one up above, they're saying x is defined as t minus 1. Y is defined as t squared. So the first thing they're asking us to do is let's get a bunch of data points. We're going to take turns plugging these guys in for t, and we can get our list of data values within this table. Let's just do that real quick, and then I'll show you how we could also take advantage of our graphing calculator. So here's our t minus 1, so I'm just going to take turns real quick and plug in these numbers in for t. So -3 minus 1, -2 minus 1, and you'll quickly see a pattern here. We're just subtracting 1 from each of those points. And so as I go down the list here, you can start filling these in real quick once you recognize the pattern. And so there's some values for x's. Our values for the y's are going to be the t squared. So I'm just going to go down and square these guys. And you will also quickly see a pattern on what's going on here. All right, it. So if we were to see these now as ordered pairs, so -4, 9, -3, 4, so on and so on, you could plot those points and come up with a graph based on those points. But that's still a limited set of points, right? We're going to be better off if we can define the entire function in terms of y and x. And so that's what we're going to do here in this next step. So similar to what we did on the last one, we would always like it to be y equals something. So what I want to do is I want to sub in a value for t right here. So as you look at this one, if I add this one over to the other side, then I can see that x plus 1 equals t. And so now I can sub this information in for t right here, and we're going to get the setup of y equals x plus 1 squared. And it's really not wrong to leave it that way. We could expand. If I square my x plus 1, we could also write this as x squared plus 2x plus 1. Right, so both of those represent a quadratic setup. It's just a matter of which format it makes more sense for as far as graphing is concerned. So is y a function of x? It is. We can see right here, this is my parabola. So y is now defined as a function of x. So we're good to go on that one. And now it would be easier to graph probably from here rather than trying to plot a bunch of data points. And so we could do that. A couple ways we could do this. We could do this by hand. Remember, we can always find the x coordinate of our vertex by doing -b over 2a. So this is something you guys have learned in the past. So there's my x coordinate of my vertex, and of course, if I take that value, plug it back into the original function, I can get the y coordinate that goes with it. I could then plot some points by picking any values, or I could even use some of those guys. We can already see right here, based on this table, here's my vertex at -1, 0. So I know that's going to be a 0 just based on what we already did here. Other thing we can do though, and I wanted to remind you of some calculator stuff we could take advantage of, would be to do that on here. So I'm going to go to my y equals. Let me clear out the old one. I'm going to plug in the new one. I could do this or this. It would be the same thing. So let me just type in x squared plus 2x plus 1. Go ahead and graph that. So there's my vertex at -1, 0, just like we figured out already. Just wanted to remind you, you can get your table of values. All of this can be given to you once you graph this graph. So I'm just going to go into my table right there. It's in blue, so I'm going to hit second and then table. And here is, if I scroll up and down, I get every point under the sun that is on this graph. And so you can always take advantage of your table in your calculator to get all those same data points that we were getting over here. So that's another option as well. Let's move on into our inverse functions. So let me flip this guy over. So here we go with inverses. So quick background on what an inverse function is. A couple ways you can look at it. An inverse function is simply a mirror image of a function across the line of y equals x. So to look at it algebraically, simply put, your x and your y trade places, right? So if you had the point 1, 2, the inverse would become 2, 1, right? And that would give you that mirror image on the other side of y equals x. So here's the line for y equals x, that dotted line, that's like our mirror. The domain and range also trade places. So because x and y trades places, naturally the domain and range would change as well, right? So you know your domain is your x's and your range is your y's. So the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. And so those guys trade places as well. So here we go. As far as symbols go, this is the notation that we would use to identify an inverse. We say f -1 of x. That represents an inverse function. So if I were to take, let's just say this is the point 0, 1. So if I were to take that same point and put it at 1, 0, and let's see if I can mirror this across that dotted line as best as I can. would look something like this. And so now you can see if I were to take my paper and fold it across that dotted line, this graph should lay right on top of the original, right? And so here I have the inverse function. So this guy is f inverse of x, just like that. You might recognize this graph. This is our exponential growth. And what is the inverse of exponential growth? It is logarithms. So this is the parent function for a log graph. This is the parent function for an exponential growth function. And these guys are inverses of each other. And we make that connection when we get into our chapter on logarithms. So give you something to look forward to there. Okay, so one thing we've talked about in the past is the vertical line test determines whether the original function or the original graph is a function. So the horizontal line test determines if the inverse is a function. So if they were to say determine whether the inverse is a function or not, we give it the horizontal line test the same way you would give a vertical line test to determine whether it's a function. So we're going to do that on this one. So we'll show you here in just a second. So if I were to graph x squared, just the parent function of a quadratic. So here are just some basic points that you would find on that. So I would have negative 1, 1, 0, 0, the vertex, and 1, 1. So here is the parent function for a quadratic. Right, and so we would look at this and we would say, is this a function? And it is because it passes our vertical line test, right? I can draw a vertical line anywhere on here and only ever hit the graph once. Is the inverse a function? Well, if you look, if I gave it the horizontal line test under the same rules, it would fail, right? Because I could draw a horizontal line right here, right, and hit the graph twice, so it would fail the horizontal line test. So the original is a function, however, the inverse would not be a function. If I were to try to show you this graphically, if I were to try to take this and reflect it, this is going to be a little tough, but let me try. If I were to reflect it across y equals x, all right, what would that look like? Right, we're going to get something, and this isn't going to be perfect, but bear with me. Right, I would get something like this. Right, that would be my inverse function, and so you could see why this would not be a function, right? So if I look at the inverse, clearly not a function, as it would fail the vertical line test. So there's two ways you could determine whether the inverse is a function or not. You can graph the inverse and give it the vertical line test, right? Or you can graph the original and give it the horizontal line test. So if the original fails the horizontal line test, that means that the inverse graph would naturally fail the vertical line test, because when it flips across that dotted line, right, it does something like this, where it would now fail the vertical line test. So you could do it either way. Typically, it's easier just to graph the original and give it the horizontal line test. One-to-one functions mean that for each x, there is exactly one y value. However, if you look at the x squared graph, it does not fit the one-to-one description, but that doesn't mean it's not a function. So one-to-one functions are always a function if it's one-to-one. But in this case, I have many different x's producing the same y value. So we would call this a many-to-one function. So that should actually say many-to-one. Right, and so that is still a function. As long as it is something to one, it is a function. If you had the other way around, if this were one to many, that's when it would fail and it would no longer be a function. So let me jump down. Oh, let me discuss that idea of domain and range here real quick. So remember what we set up above. Your x's and y's trade places when you do an inverse, right? So the domain of the original became the range of this guy, just as the domain of this would be the range of this. So one of the things that you're often asked for is they're going to say, hey, here's a function, what's the domain and range, right? And so there's a couple approaches you could do here. Of the original function, we can see that the domain Well, this would go left and right forever, right? So my domain would be from negative infinity to positive infinity. And the range of this, right, is only from 0 and above, right? It goes up from 0 as far as the y's are concerned. So we would say it goes from 0 to infinity. So if you're asked for domain and range of the inverse, well, all I have to do is flip those around. This would be the range of the inverse. You can see this inverse function would continue rising forever and continue falling forever. So it goes up and down forever, so that would be the range. And its domain would be this, right? The domain would go from 0 towards positive infinity, right? And so oftentimes, if you are asked to find the range of this, the easiest way to find it would be to actually get the inverse and find the domain of the inverse. And then that would tell you the range of the original. So we're gonna look at a little of that here as we move ahead. One of the things that you're going to be asked to do is simply to confirm whether two functions are inverses of each other. And so the main way that they want you to do that, even though it's a little bit tedious and we could probably do it in a shorter way, but here's sort of the standard book answer to this, is we simply take one, plug it into the other, and see if when we simplify it, it should come out to be just x. And if it does, we know they're inverses of each other. But they want you to test it on both. So they want us to take 4x minus 3 and put it in for that x. And then they want us to take this and plug it into that x. So they want us to do both. So I'll just do that real quick. So I'm going to take 4x minus 3 and put it here. So 4x minus 3. And then I'm just going to write the rest. So plus 3 over 4. And then they want us to take this and plug it in for that x. So over here I would have 4 and then x plus 3 over 4. Bring down the minus 3. So the idea is if I can simplify both of these and they both come out to be x, we know we have inverse functions. So if I were to clean this up, you can see that my negative 3 and my positive 3 would cancel. I'm left with just 4x over 4. I can cut the 4's, and sure enough, I'm left with just x. So definitely worked on that one. Let's look at this one. Right here I can cut the 4's. I would be left with x plus 3 minus 3, which if we simplify is also just x. So we do got a winner here. We got x's for both, which means we do have inverse functions. So let me jump over to these last couple examples here. So for this one, it's telling you how do you find an inverse function algebraically. So we're not looking at a graph right now. They're just saying, here you go, here's f of x. So what is the inverse of f of x? So really simple process. It's just 2 steps that you need to know. Step 1, switch x and y. So they're just going to trade places. So think of this as y equals 2x over 2x minus 1. So I'm going to switch my x and y. So it's now going to read x equals 2y over 2y minus 1. So that would be step 1. Just switch my x's and y's. Step 2 is just get y by itself. That's it. So it's 2 steps to get an inverse function. So switch x and y, then get y by itself. So that's what they did on this one. They started out by switching x and y. So that's what this looks like. And then they're just solving for y. This one had a little trick to it because there were 2 different y values in here. So here's what they did. They took the denominator, 2y minus 1, multiplied it over to this side. That's what you're seeing right here. They then distributed the x to get this line. They then got the y values on the same side. So they subtracted this one over. And they added this x over to here. So you're getting this line right here. And the whole purpose of doing that was the only way we can get y by itself is if I only have 1 y instead of 2. So they factored out y as a common factor. And then you can divide this piece over to here. And now you got y by itself. So this now represents the inverse of this function. So if we were to graph them, they should represent a mirror image of each other over the line of y equals x. So let's try that on a couple of our own here. So let me start with number 9. So same thing, think of this as y equals 2x over 3x minus 4. So step number 1, let's switch x and y. So it becomes x equals 2y over 3y minus 4. And then now I just need to get y by itself. And you can see this one's going to have that same trick that we saw up above here because I have 2 different y values. So my goal is to get my y values on the same side so that I can factor them out as a common factor. So I'm going to start by multiplying this over to the other side. Let me bring that up here. Let's distribute that x. And then I want to get my y values on the same side, so I'm going to subtract him over, and I'm going to add this over to here. So I'm looking at 3xy minus 2y equals 4x. Got my y values on the same side, so I can factor the y out. Leaves me with 3x minus 2. And last step is I would just divide this over to here, and we have our inverse. So let's say 4x over 3x minus 2. And that's our inverse. So we can write it this way. In the book, you probably see it written instead of y equals, they're going to say f inverse of x equals this. And that's probably a good idea because if you left it as y equals, you might have a hard time determining what was the original and what is the inverse. So by using this instead of this, we can determine which one is the inverse and which one was the original function. So these are probably the better ways of writing those guys. Last one over here. Let me give you one that's just a little bit different. So again, I'm going to switch my x and y's. So we're going to say x equals the cube root of y minus 2. And then now I need to get y by itself. So how do we get rid of that cube root? We're going to raise both sides to the third power. So it's going to say x to the third equals y minus 2. And then last thing, just add that 2 over, and we're good to go. And that would be our inverse. So that's how you find an inverse algebraically. Let me jump down to this guy. We're just going to sort of talk through this one. I just wanted you to see it. So this guy has a really important concept built into it. So really important that we look at this one. So here's the original, right? Square root of 2x minus 3. That is this graph that you see right there, right? And so that's the original. You'll see the inverse up there is going to be the reflection across y equals x, which would look like this. So we'll get to that here in just a second. So here was the original. They switched x and y. And then they went on to get y by itself, and it looks like this. So here's the inverse, and here's the original, right? So here's something that's super important to notice. If you look at the inverse function, if I graph this, what would my graph be? It would be a parabola, right? So it's because it's x squared. So this, if I were to graph it, would actually be this parabola, right? But if you look, that is not a mirror image of what we started with because it has this extra piece right here. So why, when we graph this, why do we not graph the entire parabola? Why did we only graph the positive side right here? Right? Why did we only graph that one? Well, if you look back at the original function, here was my domain and here was my range, right? So remember what we talked about earlier, this needs to become the range. And this needs to become the domain. So if you look at this, what is our new domain? Our new domain is going to say x is greater than or equal to 0. That's what they're saying right here. So if that's my domain, then I can only graph this part of the parabola, right? Because this is the part where x is greater than or equal to 0. These guys are x's that are less than 0. So we are not allowed to graph this simply because it would then break the rule of what we started with, right? And so if this was the original domain and range, then our inverse function needs to have this domain and this range to it. And that's our restriction. We're not allowed to graph beyond that. So even though this would suggest there's more to it, we're restricted by the original domain and range that we started with. So that's important that we would consider something like that and leave out that portion of the graph, right? And so, and we'll know we did it right because, I need my original to be the mirror image of the inverse. And if there's more to it, right, then it's not working. That's no longer what we started with. Okay. Let's just take a look at this here to finish it off. So just a little review of what we just talked about. So if you take a look at this one, this is what we're starting with. So let's start out by identifying the domain and range on this. Okay, so that way when we get the inverse, we'll know what our restrictions are. So as we look at this guy, what would be our domain? So remember what we learned earlier. The issue is I can't have 0 on bottom. So I know that 2x plus 5 cannot equal 0. All right, 2x plus 5 cannot equal 0. If you solve that, you'll see that x cannot equal negative 2.5. All right, or negative 5 over 2, same thing. So our domain is everything except 2.5. And I'm just going to write it this way for now, just to keep life simple. Well, that should be a negative. Okay, so then keep in mind that's going to be a restriction on the range of the inverse. Is going to be that y values cannot equal negative 2.5. If we look at the range on this, so here's where range can be a little tricky to find on something like this without graphing it actually. So one of the things that we saw earlier is, remember, this would be a reciprocal function, the ones that looked like this. Right, and these guys had a vertical asymptote and they also had a horizontal asymptote. Right, so we've looked at these graphs before. Because there is no number here, this graph is not being shifted up or down, which means my horizontal asymptote is simply here at y equals 0. Right, that would be the horizontal asymptote. Which means, if that's my horizontal asymptote, if I look at the range on this, I can see that it goes above 0 forever, and it's going to go below 0 forever. It simply won't be on 0 because of the asymptote, right? There's a boundary line right there. So I know as far as the range goes that my y values are everything except 0. So we already know the restrictions on the inverse function, right? These guys are going to trade places. This will become my horizontal asymptote. This will become my vertical asymptote, right, as we have these restrictions on the new graph. So anyway, let's go on to find the inverse. So I'm going to switch my x and y. So it's going to say x equals 1 over 2y plus 5. Let's get y by itself. I'm going to take this, multiply it over to the other side. Do not distribute. Simply because I'm now going to divide the x over to here. So we're going to have 2y plus 5 equals 1 over x. I'm going to subtract 5 and divide by 2 to get the inverse. So when I divide by 2, remember, that's the same thing as multiplying by a half, right? And so you really could leave it that way, but let's just see if we can't clean this up a little bit, put it into some friendlier terms here. So if I kind of distribute my 1/2, I'm going to get 1 over 2x minus 5 over 2. All right, and so we could leave it this way. We could get common denominators and do all that fun stuff, but this would be just fine as far as leaving it for now. So here is our inverse function, and we already know the restrictions on this. They just want us to state it on the domain of these guys. So what would be the restriction on the domain of the inverse? And like we already talked about, it would be the range of the original. So it's simply the restriction on this would be that x cannot equal 0, and you can see that would have to make sense with the way this is written. I can't put a 0 on bottom, right, because I can't have a 0 denominator. So that would just have to make sense with what we have right here. So we could have figured this out just by looking at the range. We could also figure this out really by looking at our function if we did this correctly. So that is it for this guy.